Hi, welcome to this video. If you are new to this channel, I encourage you to subscribe, and for those who are not first timers, thank you for coming back again. We've been looking at the Shem-Prashad LeetCode series, and we are currently on the 20th algorithm, which is the minimum depth of binary tree, which is what we'll be doing today. So let's get to this video. As I've said previously in the other video, please, if you have not watched the video on trees, I encourage us to go and look at that before coming here. Thank you. So here we are given that given a binary tree, and we know that a binary tree is just a tree that has just 2 nodes at most, and we have to find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. So for example, in this place, this is from the root node, we only have to go here, and then that's it. We can't go any further past this. So this is level 1, 2. So that is 2. And then at this point, we have 1, 2, 3, 1, 2, 3. So the minimum is going to be 2. For this one, it is 5 because actually it's just 2. It's just like, imagine we have 2 going to 3, going to 4, 5, 6. It's just like a linked list. Just imagine like a linked list. That is basically how this looks. That's why you see it's 5 here. Okay, so let's go to the board and see how we design this to solve this. Okay, so here we are, and we have node. Let's say 1 node here, 1 node here, 1 node here, 1 node here, and 1 node here. So we just have 1, 2, 3, 4, 5, and the shortest path we need is obviously from here to here. But you know, we're trying to find the minimum depth, so we could use the breadth first search or depth first search. Any of them could work, but I feel for this I will rather use the depth first search, since the depth first search actually prioritizes going to the depth. So for this now, it will go to the depth and find out this is 3. It will go for this and see that the depth for this is also 3, and it goes for this and see the depth for this is 2. And then what we could do is to find the minimum of all of this. So the minimum of these two, of 2, 3, and 3 is going to be definitely 2. So it knows that to be the answer. So basically, I think we have sorted it out. So we'll be using the depth first search to solve it. Now, I will use the stack because we know that is what the depth first search uses. But I'll also use recursion, since recursion also creates a stack internally within it. So we'll use these 2 approaches and see what we can come up with it too. So let's get to our LeetCode and see how we can draft that out. Yeah, so here we are, and we will first create our stack as usual. So stack, and okay, yes, I think I need to keep track of the particular level I am. Okay, so we have our stack. So let me just push our, so level 0. Is this right? Is this right? So this is 0. No. So the first level is going to be definitely 1. This is 2. So that's why we have the output here is, for example. So it means that at this point we have level 1. Yes. So this is what we'll have here. Okay. So our stack push, and then what we want to do is we want to check, go through the stack. While the stack, the count is greater than 0, we want to keep iterating. I think that is the idea we have here. So as we're iterating, what do we want to do? What do we want to do? So we want to be checking for the level of that particular node to see if so. Okay, so let me just have the level, and then I'll have the node. So basically we just want to pop what is there so that we have the level and the node, and then we know that if for example, if my node at the left and the right, so that's how we know, okay, yes, if my left node and my right node If both of them are null, then I know that I am in a leaf node. You know, if you look here, they say a leaf node is a node with no children. So it means it has no left or right. So if it has no left or right, then I know I'm in my leaf node. So I want to take cognizance of what the depth at that point is. Okay, so it means I need something here to keep track of my mean depth. And so let me just initialize it to the maximum value. The reason why I'm initializing to the maximum value is because since I'm looking for the minimum, I want to go with the highest so that by the time I find the minimum, this max will definitely not be the minimum. Okay, so we are told that the leaf node, so when at the leaf node, what I want to just do is to check if the level, so at this point I just want to check if the level, so I will just, my mean depth, I will just be using the math.mean. I want to check between the mean depth and what we have in that particular level, basically. So whichever is lower is what I want as my mean depth. So if I find a depth that is actually lower again, that's what I want to make use of. So that's what we have here. And then what do I want to do? So I have already checked. So what I want to now do is I want to put the left and the right into the stack. So stack dot push, I push in the left. Okay, so it needs a level. So level plus 1, and then the node dot left, and stack dot push level plus 1 node dot right. So this is what we have here. So we push both of them, and then at the end of the day we can now return our mean depth. So basically what we just did here, we are getting, at the beginning we put in the first depth, the first root, whatever the root is, we put that in, and then we continually go, and we are just looking for the minimum and depth. So we pop out the first item, we get the level of that, and if it is, because we only want to check the depth when we are at a leaf node, for example, where we're at 9, we don't want to be checking the depth at 3 because 3 is not a leaf node. So if we want to check it at 9, 15, and 7, for example, in this one. So at those places, I'll be checking if the depth at that level is the same as my leaf node. And then for every other one, I just want to push in the new levels and their values for those nodes, for the left and the right, and then I return this. So I think this should be good. Okay, but we're initializing this to maximum in.max. So it means if, for example, where we told it's okay, yes. So for example, we are told here that the number of nodes is from 0 to 10 to the power 5. So it's possible for it to be empty. So we just will account for that. So either I could use an if statement or, okay, let me just use an if statement. So if the root, if it is null, then I just want to return 0, because it means that there's no depth at all to go through if the root is 0. But if the root is 1, okay, yes, so I think we are good. Let's see. Okay, it's not set to an instance. Okay, so we didn't instantiate something here, right? So stack, I instantiated okay, sorry, null reference, sorry, there's a null reference. Oh, we are not checking for null here, sorry. So if my node is equals to null, I just want to continue. So let's see. So because at the leaf nodes, or even at some nodes that are not leaf nodes, they could have the left or right could be null, and I was not stopping it if it was null. So for example, if it's null at this point, I don't want to even go ahead to do anything, because if we try to do dot left or dot right, they are trying to access property of something that is null. So, and here we have it. So we submit, and hopefully everything is okay. Okay, so that looks very okay, and this is using stacks. The stack, a stack that we created ourselves, but we could use the recursion, because recursion creates stacks on its own. So let's try and look at that. So I will just comment this out and comment this. So what we could do, usually when I want to use depth first search with recursion, I always like to just create it outside just for clarity. So I'm calling mean depth DFS. Okay, and I think I need the node. Okay, so what I want to do is basically if the root is null, okay, I just want to return 0. Yes. So but if I am at a leaf node, I want to, okay, so okay, so if I am at a leaf node, okay, but before I get to a leaf node, so for each iteration, what I want to do, so I want to get my left hand. I will just say the left hand will be, so if my left hand, okay, so that means I want to return, okay, so if, because what I want to do is, if there is nothing in my left, if my left is null, I do not want to proceed. Yes. So for example, in this situation, let's say where we had, imagine we did have 9 here. So I do not want it to go to 3 and go to, this will have been null here. I don't want it to actually bother even going to that point. Since there is nothing there, don't go there at all. So if my root.left, if it is null, then let me just return in.max value. But if it is not null, then I want it to go through the min DFS again, min depth DFS, and I will just pass in the left. But I know I'm adding 1 because I know that it is 1 plus the level it is going to. So where I am now, I am at a level and I'm going to a lower level. So I am at level, at the beginning, let's say for here, when it's at 3, it says 3, and then going to the left. So I know that this is 1 plus whatever this depth we get. So, or let me use the right now. So we do the same thing for the right. For the right hand, if the right is equals to null, then we just know that there is no point calculating for that. But if it has, then we want to just do DFS again and +1. So if you look at it here, so for example, 3 is 1, level 1. It's saying that, okay, I am having 1 here, I am 1 level, so calculate for yourself 20. So 20 calculates for its own self and say 20 says I am 1, and it tells 7 to calculate for its own level. So you see 7 now if we now have at this point, if the root left is null, if we're at a leaf node, dot right is null. So if we're at a leaf node, then we just return 1. We just want to say, okay, I am at a leaf node and there's no point going below me. So since I'm at a leaf node, just return back 1. So 7 returns 1 back here. And remember we told you that this is 1 plus whatever is down here. So 1 plus 1 becomes 2. And remember this said 1 plus whatever is down here, that is 2 plus 1, that makes 3. So it knows that the depth all the way from here is 3. So that's what we want to do. But you know what we want to do? For example, 20, we send to the left. So on the left, it says, the left tells it that I have only depth of 1, and this tells depth of 1. So we have to always check. So for example, when this comes here, the depth, minimum depth here will be 3, the minimum depth here is 2. So we want to compare at every point, the left and the right. So all I would just need to do, I think, I could just return whatever my mean, whichever is smaller between the left hand and the right hand. I think this will be fine. So the minimum of my left or my right is what I want to return, since we are trying to get the minimum. And so here, I think I just need to, I think I just need to run my DFS. And I pass in my roots. I think we are good. So we are checking if it is null. So even if at the beginning there's nothing, if it's null and there's no data, it returns 0. And if it has data, then it checks if it's at a leaf node, then it knows to return 1. And then at each node, it tells it passes it to the child that I have 1 plus whatever my child has. So if the child, for example, does not have anything, if it's null, we don't bother going there. We just give it the worst possible value so that it knows that we could not calculate any height, any depth for that place because it's null there. But if it's a leaf node, then we know that definitely we just need to return 1, that I am at a leaf node and I am 1. I count as 1. So let's run this and see if this works fine. I think it should. Yes, it does. So clearly we see that the recursion is kind of more concise. It's actually simple to understand, and it's actually simpler to implement, but you must be able to understand the mechanics of the recursion here, because what recursion does is when you are doing the same thing, you are just passing it to the we're just passing it downwards to the children to also do the same thing the parent had done, but we are incrementing by one because we know that I am at a particular level. So that's how we can use the recursion for this to solve this algorithm. And from here onward, I think I'll be using the recursion wherever it is possible without using the stack. So that will be it for this. If you have any question, please drop it in the comment section. Please like, share, and subscribe, and I'll see us in the next video.